Today let us concentrate on the method, that is the exterior penalty method, and we are naming it as well the penalty function method. Now again let me just summarize what I have said in the last class, and I will just do further on the same line. Let me consider one general nonlinear programming problem, minimization of f x subject to g x less than is equal to 0. Here we are considering a sequence of unconstrained optimization problems by changing the value c j. Now, if we have more number of constraints, just like Lagrange method, we will construct the unconstrained problem this way: minimization of f x summation of c j max of 0 g j x to the power p. Now, p is positive integer value here. Now, c j values, this c j has certain property you have seen for exterior penalty function method, that is c j is approaching to infinity if we are approaching to the boundary of the feasible region, whereas the penalty function, that is p x, is approaching to 0 if we are moving towards the boundary of the feasible space. Here the penalty term c j into p j has the effect on the penalty value. Okay. Now, the c j value is always positive here. Okay. Let us see what does it mean, how the unconstrained objective function is behaving in this situation, and what is the property of the p x. Is it the penalty value is decreasing or increasing if we move from outside the feasible space towards the boundary of the feasible space. Okay. Now, we will see the properties of penalty function, objective function, as well as the objective function of the unconstrained problem. That is why we are naming this one as q c k x, and we will just prove that q value is increasing through the iterations. That is why you see we need to prove that q c k x k is less than is equal to q c k plus 1 x k plus 1. Let me consider the graphical picture of it. Now, if we remember, we have considered the previous problem x is equal to 10, all right, and for c k, say this is the graph of q c k x k. Here this is q c k x k. q c k x k means this is equal to f x k plus c k p at point x k. All right, this is the function. Say we are getting the optimal solution here, because we are searching for the minimum of this unconstrained optimization problem. That is why this value would be is equal to x k star. Okay. We are having another, if we just take c k plus 1, that is more than c k. If we consider this case, then the next function could be this one, all right, where this function would be q c k plus 1 x k plus 1, because k is changing to k plus 1. This is equal to f x k plus 1 plus c k plus 1 p x k plus 1. Say this is the optimal solution for this. That is why this value is coming as x k plus 1 star. Okay. And as you have failed that the exterior penalty function method, this is moving this way. This optimals, we are getting a sequence of optimal solutions, and that sequence, the limit point of the sequence is the optimal solution of the original problem. That is the method for this case. That is why if this is Ck plus 1 this way, now we need to prove this one. Let me start from the calculation, let me start from the value of Q Ck plus 1. I need to prove that this is better than this. Q Ck plus 1 x k plus 1 is equal to, just you see the calculations, f x k plus 1 C k plus 1 p x k plus 1, all right. Now, C k plus 1 is higher value than C k, because the methodology demands that. That is why we can say this is greater than f x k plus 1 plus C k p x k plus 1. Okay. Look at this value in the graph. Where is the value of this one? We are getting the value at, this one is the value. If I consider this as A, this as B, this as C, then B corresponds this value. Just consider instead of star, this is x k plus 1. Clear? Am I clear? Now, what you see, this B value, the functional value is higher than the A value, is it not? Okay? Because this is the curve and this curve is giving the optimal solution at A. That is why any point other than A would be the higher value than A. That is why B is higher than A. Okay? That is why we can say this is greater than Q C k x k, that is equal to f x k plus C k p x k. Okay? Then it is proved. The first condition is proved that always the q value will be the higher value if we just move through the iterations. But that does not mean that we are getting the reverse solution for the minimization problem. The higher value will guide us to get the higher optimal solution. Okay? That is very much clear from the graph. Whatever optimal solution we are getting in the previous situation, in the next situation the optimal solution will be higher than the previous situation. As the value of q is increasing, it is happening this way. Now, let me just prove the next property, that p x k greater than equal to p x k plus 1 and the other case as well. Let me draw the graph, otherwise I can put the graph this way. Hopefully, it is clear to you. And let me do the calculation with this. All right. Is that clear? Now, here I can say if I just consider one point at the top here as D, then what is the value at A? Value at A would be f x k plus C k p x k. Value at B would be f x k plus 1 plus C k p x k plus 1, because B is in the same curve. Similarly, the value at C would be f x k plus 1, that is the optimal solution in the next iteration. That is why this is we are getting for C k plus 1, that is why p x k plus 1. And what about D? D is on the curve of q c k plus 1 x k plus 1, that is why at D is at point x k, That is why I can say that f x k plus c k plus 1 p x k plus 1. All right. Now, one thing is that value at c is higher than the value at a. There is no doubt about it. See, this is p x k at point x k. All right. Now, you see value at c is higher than the value at a. That is why we can say that f x k plus 1 plus c k plus 1 p x k plus 1 is greater than value at a f x k plus c k p x k. Let me call it as 1, equation number 1. All right. And in other case, value at d is higher than a b. This is not c, this is b. All right. That is why we have written so. Okay. And value of d is higher than value of c. Is that clear? Not clear. Now, you see a and b both are on the blue curve. That is why value at b, now this is value at b I am considering, the value at c k, it should be c k, value at b. All right. Then it is okay. Now, f x k plus 1 plus c k p x k plus 1 greater than equal to f x k plus c k p x k. Now, for d and c this is the case. Now, d is f x k plus c k plus 1 p x k greater than f x k plus 1 plus c k plus 1 p x k plus 1. Let me call it as 2. Okay. Now, you add 1 and 2 together. If I just add 1 and 2, what we are getting, you see, we are getting that this part will cancel, f x k plus 1, f x k will cancel each other. That is why only we are having c k p x k plus 1 plus c k plus 1 p x k is greater than c k p x k plus c k plus 1 p x k plus 1. Okay. Or we can have c k together, p x k plus 1 minus p x k is greater than c k plus 1 p x k plus 1 minus p x k. All right. From here we know that c k plus 1 is greater than c k. All right. Then from here what we can say, that p x k plus 1 minus p x k must be less than is equal to 0. All right. Just to consider this way, because we are getting c k plus 1 minus c k, and here p x k plus 1 minus p s k, two terms differently. One term is positive, c k plus 1 is greater than c k, that is why c k plus 1 minus c k will be always positive. That is why the other term must be negative. What you conclude from here? We conclude from here p x k plus 1 must be less than p x k, mean that second result. All right. That was the first result, now it is the second result for us. Now, let us move to the third result. All right. from 1 we are getting, for having the third result, from 1 we are having f x k plus 1 plus c k p x k plus 1 greater than f x k plus c k p x k. Is that correct? Now, from here if I just consider x k plus 1 minus f x k or greater than c k p x k minus p x k plus 1, is it not? Now, you see p x k is the lower value than p x k, just how we proved it. That is why this value is always positive. Now, individual c k's are always positive. That is why from here we can say that f x k plus 1 minus f x k is always positive. What is the case then? F x k plus 1 is greater than f x k always. This is the third result as I showed you. All right. This was the first. This was the first result. This is the second, and this is the third result for us. Okay. Now, come back to the screen. As I said that these are the three results for exterior penalty function method, and we have proved it. Now, we can say that from here, as I repeatedly said, that we know the property of Q. We know the property of Q means we know that the optimal solutions of Q are always moving as c k is going to infinity, rather p is going to 0. All right. And if we just have this sequence, and if we just find out the limit point of that sequence, that will be the optimal solution of the original problem. Let us apply this method in different problems. For that we need the algorithm to solve the problem. For algorithm, the first step is that always we will start from the infeasible region. That is why we will check one point, that is in the infeasible space, and from there we will select a suitable C1, and we will find out the index k is equal to 1. Then the corresponding unconstrained optimization problem would be f x plus c k max of 0 g j x to the power p. We will just construct this unconstrained problem, then we will find out the optimal solution for that unconstrained problem. Then test whether that optimal solution satisfies all the constraint or not. If it satisfies all the constraints, that means we are in the feasible region. That is why the corresponding optimal solution can be declared as the optimal solution, as the approximate optimal solution of the original problem. Okay? Now, in the process it may happen that we are moving C not very uniformly, so that even if we just move uniformly by changing the value of p with some step length, it may happen that we will miss the boundary of the feasible space. That is why we will have certain q with the minimum value will be within the feasible space, and the algorithm says that if that point is within the feasible space, declare that is the optimal solution. That is why I said that that is the approximate optimal solution of the original problem. But fortunately, if you are in the boundary of the feasible space, then certainly that is the optimal solution of the original problem, otherwise not. All right. Now, this is now in the next we have to select if this is not optimal solution. Select another C which is a higher value of the previous C, all right. That is why consider Ck plus 1 is equal to A into Ck, all right, and go to step 2 means the corresponding unconstrained optimization problem you have to solve it. Then let us solve both the problems one by one. Okay. The first problem says us that this is the unconstrained optimization problem. That is why let me find out the value of Px. Px I can say this is 0 if x1 plus 2 x2 minus 4 less than is equal to 0. Otherwise, the value is x1 plus 2 x2 minus 4 whole square if x1 plus 2 x2 minus 4 greater than 0. All right. Let me now construct Q. Q Ckx. This is equal to minus x1 x2 if that is the original problem for us. Okay. And this is equal to minus x1 x2 plus x1 minus plus 2 x2 minus 4 whole square if x1 plus 2 x2 minus 4 greater than 0. Okay. Now, we need to find out the minimum of this. How we can find it out? We can go for the any process, as you know, unconstrained method. Otherwise, since we know this is continuous function, we can find out the gradient of this function. That is quite possible. That is why let me find out the gradient of Ckx. Then what would be the gradient? Gradient value would be, let me consider only the case where the point is in the feasible space, infeasible space. All right. For a specific C, we will consider the case where Q value is in the infeasible space. That is why if we just consider the gradient, the first one would be x minus x2 plus 2, I forgot to put the C here, that must be Ck. Okay. 2 into Ck x1 plus 2 x2 minus 4 and minus x1 plus 4 Ck x1 plus 2 x2 minus 4. Okay. This is the gradient. Now, this is the case if x1 plus 2 x2 minus 4 greater than 0. Now, gradient must be is equal to 0. If gradient is equal to 0, we are getting from here the condition that x1 must be is equal to 2 x2. Okay? Because this value is greater than 0. If we just multiply this one with 2, then it will be minus 2 x2 plus 4 Ck this one, and this is minus x1 plus 4 Ck this one. If we just equate, both will cancel and we will get x1 is equal to 2 x2. All right. Now, from here if we just solve this is equal to 0 vector, then we will get from these two equations we will get x1 star is equal to 2 divided by 1 minus 8 c. All right. Whereas, we will get x2 star is equal to 1 by 1 minus 1 by 8 c. All right. This we are getting from these two. Here c is equal to Ck. Okay. We will get it. What is the condition for the exterior penalty function method? The condition says as that if Ck tending to infinity, then x1 star, x2 star will tend to the optimal solution of original problem. This is the understanding. This is the guideline for exterior penalty function method. That is why if we consider Ck tending to infinity in this case, then the optimal solution would be 2, 1. alright, and the corresponding functional optimal would be f mean would be is equal to minus 2. Okay. This way we can solve the problem. Okay. Now, I have applied the first order necessary condition, and we can check the second order condition also to have q as minimum. That also we can find out the second order derivative, second order rather the Hessian matrix of q, and if we see that it is positive definite at this point, then we can declare that that would be the solution of the original problem. Okay. Let me move to the next problem, problem 2. Here the function q would be x1 plus x2 plus ck, etc. Again the same thing is that pk, px we can define. Okay. Now, if it is in the feasible space, that would be 0. If it is not in the feasible space, then it will be the corresponding x1 square minus x2 minus 2 square. Now, let me find out the gradient of the function q. This will be is equal to differentiation of q with respect to x1. That is why this is equal to x2 plus 4 ck x1 square minus x2 minus 2, and if we just differentiate q with respect to x2, then we will get x1 minus 2 ck, all right, x1 square minus x2 minus 2. Okay. Now, for this case, if this is less than 0, x1 square minus x2 minus 2 less than 0, what we are getting? We are getting that there is no solution at all, because from this case we cannot have the solution. Okay. Now, if x1 square minus x2 minus 2 greater than 0, and if we just equate q is equal to 0, then we will get the tuple as minus half comma minus 7 by 4 minus 1 by 2 ck transpose. All right. Now, is ck tending to infinity, this point will tend to minus half minus 7 by 4, and corresponding optimal solution we will get x1 plus x2, that is why this is minus 9 by 4. Now, what I suggest to you that we have considered the penalty function as px as max of 0 gx to the power square. Instead of that, what I suggest to you that you find out the solution for the same problem by consider at g as gx one case, or consider the penalty function as 0 mod gx, that also you find out, and for both the cases you see whether you are approaching to the same solution or not. Okay? That exercise you need to do, because there is no single penalty function. Penalty function for exterior penalty method can be different, and for different cases whether we are approaching to the same solution, if we change the penalty function, the q function will change, the pattern of q will change, but still we need to check whether we are reaching to the same solution or not. Okay? And with that, I am concluding the exterior penalty function method. In the next class, I will do the interior penalty function method for you. Thank you very much.